So let me know if you have any question. You can stop me at any time. I'm not very sure about the background of the audience. I assume we have a diverse background from information system, maybe CS and some other fields. So I was told I should give a very broad background introductions and leave plenty times for Q&A. So that's what I'm going to do. But before I start, thank you very much for having me. My name is Zhibo Zhang. I'm a faculty in the physics department of UMBC. I'm also the recent visiting fellow of the iharp. So thank you very much for giving me this chance. So I will take this chance to give you a very broad and brief overview of the abstract relation. So the concept I hope I can introduce today is the energy balance of our planet and Earth. You know, how does our planet balance the radiative energy? And what is that implications for, say, global warming and the all atmosphere circulations, weather, climate? Okay, so that's hopefully the objective for today. Okay, so let's get started. So this is slides I usually use when I gave the first lecture of a course called Abstract Radiation in our department. I get rid of some very like detailed physics, like the Maxwell equations and basic definitions, those things. But I will focus on the black body radiation and energy balance. So, and in the end, I will talk a little bit about the radius transfer in Earth's atmosphere. So, no Maxwell equations or other definitions. I will go directly to the global energy balance. Okay. So I'm not sure whether you have thought about this or if I heard about this, the global energy balance. If you think about Earth as a planet in the universe, right? So our planet needs to balance the radiation, the radiative energy. So it's like every person, right? So if we want to have a stable financial status, we want to balance our income with the outcome. So the Earth as a planet, the only way to exchange energy with the universe, with the outer space, is through radiation. So we get radiative energy mostly from our sun, right? So, and there's some other stars, but those energies completely neglectable. And we give out some energy. So we'll talk about this. There's some fundamental difference between the energy we get from the sun and the energy we give out. But the basic concept of this is, we need to balance the let's get the laser pen. We need to balance the energy. So the incoming solar energy we get from the sun must be equal to the outgoing long-wave radiation, how much energy the planet gives out to the universe. So you can imagine if you want to have a stable climate, we have a stable energy, total energy of the planet, this have to balance. Otherwise, we will have warmer and warmer climate or colder and colder climate. So at the very fundamental level, the planet has to balance the energy, right? So that's the starting point of this lecture or this talk. But there's some fundamental physics governing the energy exchange and the nature of these processes. So I'm not sure whether it still works, but at the very beginning, we're going to treat the Earth as a point. But that's a very crude, a very rough approximation. Of course, if we look at details, we will have some regions. It's brighter. For example, the desert region of Sahara And we have some region is, it's hotter, and some region it's, like a polar region, which, this group is pretty interested, it's going to be colder. But, at the beginning, let's just make a very crude, approximations and consider the Earth as a point, right? So that's what we're going to, start. But eventually, we're going to look at a more detailed energy. So this is a global heat flow. All our students have seen this many times, but it's like a must given problem in our qualifying exam. This tells you the detailed numbers of the global energy balance. So there's several things. There are many numbers, right? I just first look at the top numbers. This is what we call the top of the atmosphere. If you think about the Earth, we have boundary layers, troposphere and upper atmosphere, but at the very top, right? So that's where we can set up a boundaries and say what is the energy flow at that level. So this number is 342, and the unit is watts per square meter. Think about your typical a light bulb, right? So the watts usually used to be before we have LED, it's like 40 watts or 60 watts, right? So that's the energy. So it's how much energy is given out per unit square meter. So it's about size of your desk. So that's how much energy we get per unit square meter. That's how much energy we get from the sun. And roughly some of this energy will be reflected by cloud surface, and that's 107 watts per square meter. So the net incoming is this number minus this number, right? And so you can imagine that's equal to this number, 235. How much we get from the sun is balanced by how much we give out, in the long wave. Okay, so this is the balance. So these numbers will come back later, but this is the balance. 342 minus 107 is equal to 235 watts per square meter. But you can imagine how much energy we can get from the sun, right? So this is a lot of energy. That's why Elon Musk says we have, basically infinite energy from the sun. So this is how much energy we get per square meter, at the top of the sphere from the sun. But let's go back to this simple figure. So let's look at how much we get, right? So how much we get from the sun. So the sun is to the first order, we can imagine the sun as a black body, right? So in physics, that just means very hot, very hot sphere, right? Is emitting some radiative energy, right? So if you look at the stove, at the beginning, there's one color, it's orange, and then becomes red, and then it becomes, sometimes if you look at it, it becomes whitish. So that color tells you the energy, the temperature of the star. So usually the hotter the star is, the sun is a star, right? The hotter the star is, the bluer the bluer and the temperature, right? So if you have a lower temperature, it looks at reddish. So when the temperature becomes hotter and hotter, it shifts to the short wave. The short wave means blue wavelengths, right? So it becomes hotter and hotter, then it changed the color. So this physics is controlled by the so-called Planck function, is the black body radiation. So any stars, most stars, they emit at this follow this curve, and you can see this is the curve of the sun. So the peak of this radiation is in the visible region, right? So some scientists say this is why our eye can see the visible, because we are tuned to the highest energy density of the solar radiation. So that's where we can see most of the energy, right? So this is the region from about 0.4 micron to about 0.7 micron. That's blue to red, and that's gives the color of the rainbow. But this is the word we get from the sun. So a very important concept is the radiation we get from the sun is in the visible region, right? That's what we can see. That's visible. That's why it's called visible. We can see that. Okay. And this is the the equations we use to describe that curve, and that's also the birthplace of the quantum mechanics. But that's okay. Let's just go to the next. So if we have a very low temperature black body, like the Earth, then the Earth's radiation is in the infrared. So this is the energy spectrum from the sun, and this is the energy spectrum of the Earth. So if we look at the temperature difference between the two, black bodies, the sun, is very hot, so its radiation focused is concentrated in the visible region. That's just what we talk. The Earth, on the other hand, is much colder, right? So the in terms of degree is about 20 some Celsius degree, or 290 or 300 Kelvin. So the peak of the radiation from Earth in the infrared. Okay, sun radiation is in the visible, Earth radiation is in the infrared. So that's a very, very important concept in this lecture, right? So go back to our original plot. The energy we get from the sun is in the visible region, and the energy we gave out, Earth gives out, is in the infrared, right? So that's fundamental difference in terms of energy coming in and energy going out. Okay. So now let's look at the zeroth order balance. Okay. So the sun gives out a tremendous amount of energy, right? It's unmanageable amount of energy. We only get a very small fraction. Okay. Let's think about this, right? So if we build a sphere around the sun, right? So if we have what is called Dyson sphere, right? So if we build a sphere around the sun, this is how much energy we get at the unit, at the surface, right at the surface of the sun, right? So this is 10 million watts per square meter, right? So that's how much energy. This is not what we get. Instead, we only get a very small fraction at the orbit of Earth, right? Earth is orbiting around the sun. So think about if we build another sphere at the orbit of the Earth, then how much energy passing through the Earth's surface, the sun's surface, must also passing through that sphere, right? The sphere at the surface of the sun, that's the Earth's orbit. So we can do a simple scaling. So the scaling is 4 pi r square of sun. This is the surface area of the sun times the energy density at the surface of sun. That is equal to the energy at the Earth's orbit times the energy density at the Earth's orbit, right? So then we can get the energy density at the Earth's orbit, right? So this is what we call solar constant, right? Imagine the Earth is just small object orbiting around the sun, and that's how much energy we get. So this is called energy. This is solar constant. Every planet of the Earth, of the solar system, has a solar constant, right? Like Jupiter, Saturn, all of planet, we have a solar constant. That is the energy density from the sun at their orbit. If you are further away from the sun, you get less energy. If Mercury, for example, get most of the energy because they are so close. It is so close to the sun. This basically, you can imagine this how much you stand in close to the bonfire, right? If you're getting very close, you feel very hot, but if you further away, you feel you don't feel very hot, right? So this is the number solar constant we get at the unit square meter of the Earth orbit. We get 1,366 watts per square meter. Imagine that, right? Every unit square of a square meter of the area, we get 1,366 watts, energy. Every second, this much of energy passing through that. That's amazing how much energy we get. And that we only have one area. If you think about sphere, the cross section of a sphere is about pi r square, but we have to distribute that over the whole surface of the Earth, right? So that's why this number has to divide by 4 pi, right? So how much energy we get? We get pi r square. We have to distribute over 4 pi r square. So this number divided by 4, right? So that's the number we have here, right? This is 100 1066 divided by 4, right? So there's a variability, right? So that is not a constant. This should be 1368 divided by 4, but that's very close. This is the number, is the solar constant divided by 4, right? That's because we are uniformly distribute how much energy, total energy we get from the sun divided by over the total area, surface area of Earth. This is that number. It's our solar constant divided by 4. Okay, so that's how much energy we get in this figure. Now let's do a simple test. So as remember, we have incoming solar radiation, we have the outgoing thermal radiation, right? If we assume, Earth is just a black body, just like a black body, how much energy we get, we give out at that energy at a black body radiation, right? And what would be that temperature? This is the black body radiation. It's emitting as the 4 pi r square of the Earth. So, and we can easily calculate this. This is a very, primary math, and we can get a number that is, surprisingly cold, right? So it's minus 18 Celsius degree, right? Why is that, right? So why do we have this? If the Earth is a black body, if only the Earth behave like a black body, then we have a very low temperature. But we will see that that's because of to the first order the greenhouse effect. So the greenhouse, like water vapor, carbon dioxide, all the greenhouse gases keep us warm. So we will talk about that later. But I think this is the stop of our first part. We established basically the energy balance of the Earth, right? So to the first order, this is the energy we get from sun, the solar constant divided by 4, right? So, and this is how much the Earth reflect, and the cloud, the surface, this is how much it reflect. And this energy, 342 minus 107, is equal to how much energy we gave out, right? So this is to the first order we have this balance. But of course, internally, the Earth system is a very complicated system, right? So there are some will be absorbed in the atmosphere, and the atmosphere will emit and give back to the surface, and that's we're going to talk next. But I will make a stop here and see whether we have any questions before I go to the next to talk about, for example, the greenhouse gas. How long should I talk, Josephine?
We were hoping to leave about 10 minutes for questions at the end. So,
okay.
Yeah.
It's so deep. I'm sorry, going to talk to, or it's just me?
No, I mean, if you prepared the lecture or the workshop, it's up to you. You can, if Sudeep has something to share, you can always also interject at any point. Yeah. But
well, I think radiative transfer, it will take a long time. It's not that, but at the same time, it's very important. So let him continue. Maybe
Okay.
it's very important.
Yeah.
Okay, I can stop anytime. I don't have to go through the whole lecture, but it's up to you. I don't know. I can talk more, of course.
No,
but any question from students or?
Aloy? Please.
Yes, I want to go. So, Dr. Zhang, just you have shown a lot of equations. So I can recall for my 12th grade physics, some of the equations, they are similar. At the time, I have also read these equations. So my question is, as you are working on the data science or machine learning, that has been already applied to these equations to build any machine learning model so that will help us to better the radiation systems. It has been already applied, or you are planning to apply?
Oh, this is very basic things, right? I'm not sure we are there yet. This is like understanding the physics, right? No matter how I think the machine learning is, we still have to understand the fundamental physics, right? So this is, I hope it give you some fundamental knowledge of this. And I can show you some of our applications of machine learning later on, but not yet. This is, but I hope you know. Perhaps you have heard about this. The physically guided physics, what do we call physics guided machine learning? So, for example, we teach the machine learning how to conserve the energy conservation, right? So, and that's a very important concept for machine learning. And machine learning can give a very good regression, but it's still the energy may not be balanced, and even small error in energy balance can be big consequence, right? So that's something, you know, if we understand this, then we can better get the machine learning. Yeah.
Thank you. And another question is just sorry.
Sure.
So,
Yeah.
So basically, like sun is the source of lot of energies, right? So if we can make a sun in our own, like artificial sun, is it possible? Do you think from the radiation? Because as you are doing research on that.
Oh yeah, you're talking on the fusion, right?
Yes, yes,
yes. Yeah, it's a fast developing field. I've heard some very exciting news, and have been hearing exciting news for many years, but it seems to be like 20 years forever, right? So, but we are optimistic. You know, I believe there's going to be one day we're going to have a fusion. It's like a man-made sun, right? So and controllable. We already have that. It's the bomb, right? It's a bomb, but you know, it's we have to control it. We already have that kind of energy, but just it's not controllable. Yeah.
Thank you.
Yeah, good question. Okay. So let's go to the next. Just talk about. One more concept I want to talk about is global warming. I think that's very relevant to this group and to what we are doing. So if we think about the energy, right? The energy has to balance at the top atmosphere. It also have to balance at the surface, right? So we are living here. We are living at the surface. So, you know, as a boundary of this atmosphere, at the inner atmosphere, at the top and at the bottom, at every place the energy has to balance in the long term. It doesn't have to balance at every second or even at any year, but for the long term, if you observe this for thousands of years, you know, or at least hundreds of years, this should be balanced, right? So this is what we will talk about next. Okay. But if you think about these processes, so because we just talked about the incoming radiation is visible and outgoing in long wave, the atmosphere are playing also different role in this two spectral region, right? Visible, as we see today, if you look at the window, depending where you are, if you're in Maryland, you see a beautiful day. There's almost nothing between you and the sun, right? If you look at the sun, it can hurt your eyes, but that's because the atmosphere without cloud is mostly transparent. The sun can directly go from the very top of the atmosphere all the way to the surface, right? You don't see too much energy loss, right? So other than reflection, if there's no reflection, most of it will go down. But if you look at in the infrared region, right? So this is how much energy the surface giving out, right? So this number 390 is much higher than the 235, right? So in other words, the energy balance at the surface is much stronger at the energy at the top atmosphere. And this is only possible because of the greenhouse gases in the atmosphere, because greenhouse gases give back. You see this arrow here? It gives back a lot of energies. So that keeps our warm at the surface. But let's go just step by step. I'm not going to go through all these equations, but you can imagine the Earth's atmosphere behave very differently in the visible region and infrared. So this is a very good plot. You can see that. The red curve is how much energy we get at the top of the atmosphere. The shaded area is how much energy we get at the surface, right? And this is the spectral region from about 0.2 micron to about 3 to 5 micron. You can see most of the UV region is gone. Anyone know why is that? You put on the sunscreen. Why is that?
Prevent sunburn.
Sunburn, right? Most of the sunburn, the black is the UV region, and we are lucky that there's not much radiation at the surface, and that is because ozone layer, right? So we talk about there's ozone hole, a while ago, and now it's not a hot topic anymore. But when I was a student, there was a lot of research about the ozone hole. So there's a big ozone hole, that's caused some troubles. But on the top, in the very atmosphere, we have an ozone layer. That ozone layer absorbs a lot of UV energy, right? There's some UV energy passing through, and we need sunscreen for that, but majority of that energy is gone. That's this difference between the top atmosphere, this curve, and what we have in the surface. The UV, ultraviolet energy is gone because of the ozone layer. But other than that, you can see most of the energy is kept, right? It remains from the top atmosphere to the surface. That's what they are talking about. The atmosphere is mostly transparent in the visible region. We get most of energy from the sun. Okay, there are some dips here. So those are what's called absorbing band by atmospheric gases. Some atmospheric gases, including water vapor, it absorbs. Water vapor can absorb, visible light, and it can absorb a lot of other, infrared and microwave. The water vapor can absorb water. The microwave is how we microwave our food to make it hot. But that's because of absorption of the water in your food, and it absorbs energy from a microwave, so keep the food hot. But water vapor can also absorb energy in some other spectral region. But other than that, it's mostly remain the same from top atmosphere and the surface. But if you look at this part, is the infrared. These different lines are the emission at the surface, at the very surface. If you have a different emissions, that's the curve. This shaded curve is how much can passing through the atmosphere and reach the top atmosphere, right? So here is how much is top and how much is surface. This is in reverse because we are outgoing. So this is how much at surface and how much can passing through atmosphere. And you can see only a small fraction is left, right? So most of the other part are absorbed by, water vapor and especially carbon dioxide and other, greenhouse gases, like methane and nitrate. So this energy is in the window region. This is what we call the window region. Window region. It's how energy can escape the atmosphere. So this is the infrared, right? So the atmosphere is very opaque. It absorbs a lot of energy, in the infrared region. So this is the difference of atmosphere behavior. And because of that, so we have a very different energy balance. So this is just, to show you how we have a different absorption. So we don't need to go through this. It's the, change of the quantum state of the molecules. But the result of the infrared absorption is a greenhouse effect, right? So if you think about, we have the atmosphere is like a blanket, right? So it absorbs the radiation from Earth and then give back that energy to the Earth's surface. And that can keep us warm, right? So if you think about this, the solar radiation is mostly transparent. It goes in and reflected some, but mostly, transparent. But atmosphere in the infrared, you absorb a lot of energy, and this two arrows shows the emission of atmosphere, right? So the emission of atmosphere, it will give back some of the thermal radiation. And because atmosphere has a lower temperature, so this number plus this number is lower than if you only have this, Earth radiation. Can you see that? Because the temperature of atmosphere overall is lower, and the thermal emission is mainly sensitive to the temperature of a layer. So this, atmosphere radiation plus what passes through the atmosphere is smaller than the Earth's radiation. Okay. Some more equations, but in the end, if you consider the greenhouse effect, you will have a reasonable surface, right? If you consider the transparency of atmosphere, and you can get closer to normal, about 13, 15 degree temperature. Okay. So now let's go back to this curve, right? So I'm gonna spend a few more minutes here, and I think I can stop for Q&A. So remember this number. This number is what we call solar constant divided by 4. This is how much energy we get from the sun, right? And so this energy passing through atmosphere, and some of them is absorbed by atmosphere, some is reflected, some is reflected by the surface, right? And over this side is the infrared. The infrared, we have a surface radiation, it passing through the atmosphere. A lot of them is this energy is absorbed by the atmosphere, only a little bit passing through, but the atmosphere also emits some of that. And combining all of them together, you have this 235, and this is balancing this radiation, right? So, but if you look at the surface, the energy balance at the surface is at a much stronger intensity than the atmosphere. That's why the surface is warmer than the top atmosphere, right? So because of the greenhouse gas effect. Now let's do a thought experiment. If suddenly we increase the greenhouse gases of the system, right? We suddenly increase. That is equivalent of increasing opacity of the atmosphere, right? So we suddenly make the atmosphere more opaque in the thermal infrared, just like instantaneously, right? So and compared to the Earth, the human history is really short, so it's equivalent of instantaneous increase. Which number will change immediately?
Maybe the bottom number.
If we change, we don't change anything yet. We just change here, right? Atmosphere, we increase the greenhouse gases suddenly, let's double it or triple. We almost triple the CO2 level already.
The lower numbers would
Which one?
increase. 390 will probably increase.
390. We don't change the temperature of surface yet. We only change the amount of the greenhouse gases in the atmosphere. Just we suddenly double that. Which number change immediately?
Back radiation. Is it 324?
324. Not yet. We just increase the that will increase, right? Like, because emissivity will increase, but that's not the major change. What is the major change? If you think about it, right? So if you have looking at the screen, right? You put some kind of screen in front of you, make the screen darker. What number change immediately? So let me give you a hint. One of these three numbers will change.
340. Oh, 107 might change because when 342 hit the blue layer, a little more than 77 was reflected back.
Why is that? The atmosphere is transparent, visible, right? So no matter how much we give it in the atmosphere, is still transparent. I see someone type the 335, 235. That's a right answer. Can you explain why?
Francis, can you share? His microphone is working.
Okay. But so yeah, that's the right answer, but anyone knows why? The 235, how does it change? If you think about it, if you increase the opacity, increase the greenhouse gases, if you increase the opacity, how opaque the atmosphere is, you make it more opaque. Suddenly make it more, yeah.
Maybe because it's like redirecting the long waves from the sun, and that's why it's increasing.
Yes, think about this, right? So this is more like a gate. You have a water coming in, you have some filter, or you can imagine it's a gate. That gate modulate how much can go through. Right? That's the opacity of the atmosphere. If you have water comes in, you have a gate. If you open it larger, it will more go out. If you make it smaller, the gate smaller, if you have less go out. That's opacity of the atmosphere. Right? So if you increase the greenhouse gases, you increase the opacity of the atmosphere. It is equivalent of making that gate smaller, right? That makes sense? And if you make that gate smaller, what happens? Which number?
235 will drop then.
235 will drop, right? 235 will drop, right? So that's exactly what is happening over recent years because of the greenhouse gas increase. We're reducing the outgoing long wave radiation, right? If we suddenly this number drop, suddenly this number drop means what? It's no longer balanced, right? How much give out is no longer equal to how much we get. We get more or get less.
There's a question again.
So because this number drops,
Mhm.
we get more energy or do we lose more energy?
On the Earth's surface, we get more.
Right, we get more energy, right? Because this number drops, now we get more energy.
Yes.
So when a system get more energy, what happens? It becomes hotter and hotter, right?
Yes. Mhm.
And when it becomes hotter and hotter, what happens? Which number will change?
Oh, the bottom one will increase.
They will increase. Now you have more water goes in. Even though you have a smaller gate, you have more water go out. Even you have a small gate, this number will gradually increase.
Ah.
And it will reach the balance again, right? Let me say this again. When you have a greenhouse gases suddenly increase that, this opacity on the sphere will becomes more opaque, right? And suddenly this number decrease. And now we have more energy into the system. It's equivalent of, make the energy escape gate smaller, tighter. So this number will drop. But how the system achieve a new equilibrium, new balance again, is because the system becomes hotter and hotter. So this number will increase to the first order. It will force more energy, generate more energy, right? And then until this is balanced again. There is one planet in the solar system, this process has gone crazy. It's Venus. Okay, so if you look at what happens in Venus, because Venus has a lot of greenhouse gases in the atmosphere, so the surface temperature is extremely hot. But because the atmosphere is so opaque, very small energy can go through. And what happens, the temperature becomes hotter and hotter until it can balance the net incoming radiation again. So that's nutshell of the global warming. Okay, so we suddenly decrease the opacity of the atmosphere, so we have more incoming energy, and the system is trying to get a new equilibrium by generating a higher temperature and more radiation out until it achieves the balance. Okay, that's like a 1,000-mile high summary of what's going on, but because there's definitely much more things in the greenhouse gas and global warming. But I'm gonna make stop here. I think I have talked a lot, maybe too much. And do you have any radiation or anything related question?
We open up for questions, or could we go 10 more minutes? Perhaps we can continue. And then
Tired of this? Okay. I hope you can have some questions, right? I can talk. I'm a teacher, right? I'm a professor, so I can talk, forever. But I hope you can have some questions. But okay, so if you want more, but I have some more. So far we talked about the infrared part, right? This part of the spectrum. Of course, there's also interesting things going on in the visible region, right? So in the atmosphere, we have a lot of particles. Those particles, are aerosols like smoke and dust. This is a dust plume, dust storm, pollutions, and also cloud, right? So this is in east part of China. There's a lot of pollutions, and then you can see even the cloud becomes like dirty, right? So so that's the particles in the atmosphere. So and that's also one area our group studies a lot is how the particles, especially cloud and aerosol, interact with radiation in the atmosphere. So the one way the energy exchange with the particles is through scattering, right? So I'm not going to go into details, but just to give you some examples. When we look at the sky, right? The sky is blue, the cloud is white, right? That's because the blue sky is due to the Rayleigh scattering, right? The Rayleigh scattering scatters more shortwave energy, the blue energy, than in long wave. That's why when we look at the sky, we see most of it's the Rayleigh scattering. When we look at the cloud is so-called me-scattering, is a white, right? The cloud looks white because of the scattered energy is neutral. If you see more radiation from red wavelengths, then the object appears white, right? If you have more light from the blue, then the object like the blue sky looks blue. But the cloud is scattered energy almost equally, so it's white, right? So it's white. And so also you have a rainbow, right? And this is the scattering of the droplet, and in high school maybe you learn this reflection and refraction. So this is the sunlight goes in, and because of the refract index of water is different at different wavelengths, so you have a different reflection and refraction of the light. But you can see you have a rainbow. So by the way, when you see the rainbow, anyone can recall where is the sun? This is a picture we are looking at the rainbow, right? If you recall your experience, is the sun in front of you or behind you? Anyone remember last time you see the rainbow? Whether the sun is in front of you or behind you?
I can't remember, but I think it should be behind you.
It's behind. Yes, it's behind you, right? So that's because of the scattering. This angles is in the back scattering direction, right? Forward means if you look at the sun, that's right away you see that's a forward direction. But the scattering, this reflection is reflecting back. So that's the peak, right? So this is a very strong forward direction. This is the back direction, and this is exactly back scattering direction. So in other words, when next time you see the rainbow, remember the sun is behind you. That's also why you usually see the rainbow in late afternoon or early morning. You don't see that in the middle of the day, right? That's because the sun is too high. You have to fly the airplane to see the rainbow. So imagine that the plane, if the sun is too high, the rainbow is up in the sky. You have to be, in a airplane to see that. But if you late afternoon, then you can see the rainbow. Okay, and also the rainbow color. This is what if you're lucky, you can see secondary rainbow. So actually, there's many layers of rainbow. So UMBC just launched a satellite can observe the rainbow from space. Okay, use that to retrieve the cloud properties. But that's the scattering of the cloud in the atmosphere. So I'm not sure. So this is a I think it's a energy, and this is a global cloud cover, and it's from a satellite. NASA has many satellites. One of the satellite monitors the global cloud distributions. So it is not distributed evenly, right? And I don't know. I'm sure many of you are from different locations over the globe. and you can pick up your hometown or a favorite location to see where, you know, whether the cloud, how the cloud change. So in this animation, the whitish color is the cloud. You have a lot of cloud. It's basically it's overcast cloud. When you see dark blue region, that's where you almost have no cloud. Okay, so look at some places how the cloud will change over the month. Right, this is how it changes. And you can see over some region like a Sahara region, right? So there's desert region, so there's, you know, almost always no cloud. And if you're over, you know, Amazon basin, mostly you have a lot of cloud. But over ocean, you can see this region. That's called ITCZ. You know, that's where, you know, Northern Hemisphere or Southern Hemisphere, the air converge. That's, you know, where you have this very, very thick cloud and a lot of cloud. In some regions, for example, India, if you look at India, at different months, you will have a very different behavior of cloud. Some season, if you see here, you have a lot of cloud, right? So that's the July, August, and some region. In some season, you will have very less cloud, for example, January. Okay, so I'm not sure whether some students from there, what is that cause of that?
Dr. Zhang, it's the monsoon season.
Yes, exactly. Yeah, that's the monsoon, right? So when you have a monsoon, you have a lot of cloud. When you have that monsoon, can give you dry season and wet season. That's the monsoon, and you can see some other regions too. You have the monsoon, like an African region. Some of that is also controlled by the West African monsoon, and some Asia region. Here you also have some monsoon, you know, but especially in India, you have a lot of cloud and impact by monsoon. Over the polar region, if you look at, for example, Greenland region, so you will also see the variation of the cloud, and some studies suggest the cloud may have the impacts on the melting of the Greenland, but you know we don't have time to go through that. But usually you can see that the driest and the hottest region is the Sahara region, and over here and some part of Peru. And this is where the descending region of the circulation, right? So when you have the air goes above, and if you squeeze out of the water, and that water heats up the air, and when it goes down to this, you know, Sahara and other region, and you have a lot of, that's where you have a lot of desert. The air there is dry and hot, right? So that's those region. And this is the aerosol. That's where you have a lot of aerosol. If you look at this region, is the dust. You can see that the Sahara dust will outflow, goes here, and sometimes you can go all the way to the east coast of the United States. And over Amazon basins, most of the time it's clean, but when you have a lot of you know, fires, you know, Amazon basin, that will generate a lot of smoke, and that's where you see a lot of those aerosol, right? So in this time, there's a lot of fire here that will generate a lot of aerosol. Some region, you know, for example, the east part of China and India, for example, there is a lot of pollutions, you know, from the industry or, you know, just our daily life, and that will also generate a lot of aerosol. Okay, that's air pollution. So this is, you know, how all these are generated from the satellite, and also tells you, you know, where you can find a lot of cloud and aerosol, and those aerosol and cloud also play a very important role in that picture we just saw here, right? Because cloud reflects a lot of energy, and so does aerosol. So they also play an important role in this picture. It's part of this 77 reflected. You can imagine, right? So if in the future, if you have a warmer climate, if this number change, but simultaneously, this number will also increase, right? How much reflection will increase? Then it will achieve balance, right? Without getting hotter. If this also increase, this decrease, then we can achieve a new balance, right? So that's the so-called feedback. But that's also possible if you increase the cloud, or if you increase the aerosol. And there is a dangerous and but very fancy word about geoengineering. It's all kinds of crazy, not crazy, but interesting ideas to release some aerosols in the atmosphere, or we can make the cloud brighter so we can reduce the greenhouse effect. We can balance the greenhouse effect so we don't have a very strong global warming. Okay, so I think I have talked too much. I will leave the rest of 10 minutes for any question or discussion. Yeah.
Thank you so much, Dr. Zhang. We could have you talk for forever because this is very insightful. Just open up the questions a bit while others are thinking about what to ask. So from this diagram right here, what are the contribution, or what can you allude to the contribution of partly the opacity within the atmosphere? Is it more natural or more human engineered, in your opinion? And how has that changed over time?
That's a very excellent question. That's an excellent question. So in terms of total contribution, like a total amount, right? So anthropogenic greenhouse gases, the man-made greenhouse gases, is a very small amount, but that is a perturbation. So in other words, if you think about this, right? So we already have a balance. How much we earned, you think about your credit card, right? Already how much you have a very balanced, money, right? So you earned $1,000, and you spend $1,000. But suddenly every day you have an increase of say $10, right? And that's a small amount, but it's an imbalance. Right. So, and that will cause trouble because every day you will lose $10, right? So in other words, the system has already balanced because before the human, right? If you think about it, the system is balanced. But now if you have an anthropogenic, we perturb that balance, we destroy that balance, and that is causing the trouble. In terms of global warming, right? The energy we perturbed is only about 1.5 to 3 watts. That's how much energy we perturb compared to 235, right? That's my analogy. You have $1,000 balance, but that $1,000 is balanced. How much you earn is equal to how much you spend. But now if you add it to $10, it's a small amount, but it's an imbalance. But remember, this 3 watts is everywhere on Earth. Think about how large the Earth is, right? And times the surface of the Earth, that's a tremendous amount of energy. And you're accumulating every second, right? So, but go back. Yes, it's a small amount, but it's an imbalance.
Okay. Thank you. Any other questions?
Yes. I'm particularly interested in the previous slide about the numbers.
Yeah.
I'm wondering, I thought 390 would be the first figure to change before 235. Why is it that 235 changes just before 390 if we increase the opacity of the atmosphere? And also the opacity of the atmosphere, why wouldn't it change the amount of solar radiation reaching the Earth's surface?
Okay. Let's answer the second part, right? Remember the atmosphere is transparent, right? In other words, to the first order. All I'm talking about here is to the first order, right? Very crude proxy. So in other words, the greenhouse gases does not absorb any visible light. It only absorbs the infrared light.
Okay.
So no matter how much you add, it doesn't affect the solar visible light.
Okay, I get it.
Okay, so get it right. So the first question, right? So this system is adjusting system, right? So we have to think about, in terms of what happens first. If we have to think about this, what happens first? The change of the greenhouse gases happens over just last about 100 years, right? It's about 18 sometime to now. It's about 18,000 times, right? So that is a very short time. Consider if you think about hundreds of years, 1,000 years energy balance, right? So that's almost like an instantaneous change of the shared opacity. So, and that adjustment of radiation adjustment is turned at the speed of light, right? But the surface warming, you have to have absorbed, and then you will have some wind will blow this through, and there's some precipitation. So that adjustment is much slower than the radiation balance. That's why this number to the first order, you can imagine it will change first, right? And then after the system becomes imbalanced, the system will start to, try to find the equilibrium again. And that's why this number will increase and balance this, radiation again.
Thank you. That's very informative.
Yeah. All I'm talking about is to the first order, right? So, to simulate this, we really have to have so-called global climate model. We have to take into account of, like, for example, the water cycles, right? We have to take into consideration the wind, the ocean circulation, right? It's extremely complicated, but, given we only have, 50 minutes, and this is only one lecture, so I can just approximate that in this very simple diagram.
There's a question here. What kind of research avenues are open for data scientists to study the Earth's energy? I believe that should be balance or the imbalance in it. And
right, so in reality, this has to be monitored by satellite, right? How we can get this number, all these numbers, we have to have observations, and also we have to have modelings and analysis. For example, measurement of this number is extremely difficult, right? Remember, the energy we talk about is about 1 watts, right? And out of 1 to 3 watts out of this 200 or 300, number. So it's a very small number, and we have to collect a lot of data to be able to tease out this imbalance, right? In other words, the imbalance is to a very large balance number, right? So that's where we need to have a data science. We have to dig into tons of data to find those. We have like put all the pieces together to find that little unicorn in the picture, right? So that's where we have to have a lot of data, and we have to look at many different methods, and they all converge to the same answer. Then we can trust the results, and because of that, we need data scientists, machine learning, so all these different techniques. Yeah.
thank you so much. We're right at 5 o'clock. I know Malloy had a question. Malloy, you can always send that question unless. So thank you so much, Dr. Zhang. This has been very, very informative. We
Okay,
hope
I'm
we
glad
can
it's useful.
we
Okay.
can have a second lecture sometime, because I know you must have a lot to cover, and our students have a lot to learn. In fact, we all have a lot to learn from this, especially how it's related to iHerb. But we want to, thank you for your time, and for whatever you have shared. Very helpful. Appreciate
Okay.
it.
Thank you very much. Thank you.
Thank you, everybody.
Thank you. Bye-bye.
Thank you. Bye-bye.
Thank you. Bye.
Thanks.